So we finally come to the point where we're going to define derivatives of functions not from subsets of the real line to a vector space, but between two vector spaces. So functions from Rz to Rk, from the space of continuous functions to itself, or from any other vector space to any other vector space. So any vector space to any other vector space. You see what I mean? And you'll have to bear with me for a little bit. We'll try to make sense of an expression like this, right? So x here is a vector in some v, so is age. And O of age, we're going to see is a remainder term. Which basically what we want is that O of age divided by age, norm v, goes to 0 when age goes to 0. And the main question, though, is how to make sense of this guy here, right? So, okay, I should have said this before, but always I'm going to be assuming that I have a function defined over a subset of vector space V to W. So that's going to be our setup. So we want to describe f locally, that is for small h, in terms of f of x, with value at a point x, plus some term that depends on age, and some remainder term that should be small, right? And as I said, the main mystery lies in this guy. So how do we make sense of this? Okay, just to make sure we all know where we are, we're always going to assume that V and W are Banach spaces with their respective norms. The domain of the function f is going to be an open set, and I'm going to try to clarify why that is later. And so we have this function from an open subset of V to W, and we have a point in U, in the domain, and we want to make sense of this phrase, right? So f is differentiable at x naught. Of course, we don't want to make sense of it in any way, in any kind of random way. We want to have a definition of derivative that gives us good properties. What are the good properties that we have for the usual derivative? We have things like the chain rule. We have many theorems saying that, well, if a function is differentiable at a point, it's continuous. If it's differentiable with bounded derivative over a set, then it's Lipschitz. So we want to have some of these things, right? So at the very least, holding in our case. And this good property, all these things are related to local properties of f around the point x naught. So we want to have a strong enough notion of derivative that allows us to have, whenever f is differentiable, that gives us non-trivial properties of f in the neighborhood of x0. Okay. But as we're going to see, there are kind of natural attempts of at finding such a definition that fail, right? And it's nice to try them out before we go for the real thing. And the first one, perhaps kind of the main kind of contested against the good notion, is this guy here, the directional or Gâteau derivative. So this derivative is defined as a limit, and it's a limit of the same kind where we define derivatives from, this should be 0. It's a limit of the same kind that we define for functions from the real line to a vector space, right? So the numerator here belongs to W. It's a difference between two elements of W. And I divide by t. And if this limit when t goes to 0 exists, this is called the directional derivative in the direction of v. And sorry, there's one more thing I need to take a plus here. So what this is saying is this. I'm going to look at, I have x naught, I have vector v, and I'm going to look at the variation of f along this line, or actually the semi-infinite line that starts here, goes in this direction. So the existence of this Gâteau directional derivative means that if I think of the restriction of f to this line, it's a differentiable function in the sense of functions from a real line to W. And of course, this definition makes sense. It makes sense to take this limit because since U, the domain, is an open set and x naught is an element of this open set, That means, as we all know by now, that there's a protective bubble around x naught of radius r that's entirely contained in the domain, meaning that if I look at x naught plus tv for v small, this is also an element of the ball and therefore an element of u, right? So it makes sense to take this limit. And another thing about this limit is that if you think about it, let's assume temporarily that we have v, right, for this item here, we assume that v is equal to rd, and let's say w equals r. If we look, right, so rd, unlike other vector spaces, has a natural finite basis consisting of the canonical basis vectors. And if I think about the direction derivatives, in these specific directions, these are the partial derivatives from calculus, right? So if I look at f of x naught plus, right? So if I look at x naught plus t times ei, then I'm looking at how much the function changes when I only change the ith coordinate of x naught. And therefore I get the partial derivatives. Well, that's basically true, right? Because I have this plus here. But if we forget about the plus, then we basically have the partial derivatives back. And we're going to be talking about partial derivatives in later videos, so but I mean, as we're going to see, partial derivatives are kind of a way to compute derivatives, or the real derivatives we're going to define. But as we're going to show in the next slide, having partial derivatives, or even having directional derivatives in all directions, is not enough to guarantee that a function is differentiable. And we're going to show that by an example. The example is this specific function. So you have a function from R2 to R. Well, I mean, it's equal to 0 when you're at 0 in R2. Otherwise, it's equal to this fraction, right? So here, remember that a vector in R2 is hash coordinates x1, x2. So this is the ratio of first coordinate cubed to the sum of the two coordinates squared. My claim is the following, that this function has well-defined derivatives, directional derivatives at 0 for all possible v, and these are actually all 0. However, this function is discontinuous at 0, because if I compute it along this curve t and t squared, this ratio blows up. Okay, now let's try to make sense of this, right? So first of all, why am I saying that this is very bad? Well, I told you that a good definition of the derivative should be such that if I know a function is differentiable at a point, then I know it has some nice properties, right? So one very basic property of derivatives of functions defined over the real line is that if the function is differentiable at a point, it's continuous at that point. And here we see that a function can have directional derivatives in all directions and still be discontinuous at a point. Okay, so now let's see what happens, right? So here I have this function, and let's argue that the directional derivative exists. I mean, I'm only going to look at vectors that are non-zero, simply because the directional derivative when v is equal to 0 is always 0. That you can check by yourself. Right, so remember that f, so I need, f is 0, right, so it's 0, so I need to compute the limit when t goes to 0, plus of f of t times v divided by t. Well, I should subtract f at 0, but f is equal to 0 at 0, so there's nothing to be done. And okay, this you can do by hand, right, so you're going to get t cubed x1 cubed x1 squared, but v1 cubed. I get here t squared x1 squared v1 squared. Sorry about that. So I t squared v2 squared, and I multiply by t. So if you see what you get when this is exactly equal, right? So this, well, okay, forget about the limit. This is exactly equal to the first coordinate cube. So I said it was always going to be 0, so that's not true. That's not. Sorry about that. I made a mistake here. Basically, this is what you're going to get. That's for all t, and therefore the limit when t goes to 0 plus is the same limit when t goes to 0 plus. And you see this limit is well defined whenever the vector v is non-zero, because then the denominator is non-zero. It's very good shape. So if v is equal to 0, then you just compute the function, and you're going to get 0. Therefore, there's nothing. It's also differentiable when v is equal to 0, as I said. Okay, well, how come this is not continuous at 0? Well, if I compute f at a point with coordinates t and t squared, what do I get? Well, I get t cubed in the numerator. In the denominator, I get t squared plus t to the 4. And when t goes to 0, this goes to infinity. Therefore, f is not, right? So with an infinity is not 0, which is f of 0. So what is going on here? Well, if we look at the plane and we look at what's happening with this function, here's what I've just shown you. I've shown you that if you look at straight lines and you converge to 0 along these straight lines, then f is very nicely behaved. Not only is it continuous, but it's also differentiable along these straight lines. However, there's this curve here, which is t is t squared. And along this curve, if I go to 0, then f is very badly behaved. So, and this is really the problem with these directional derivatives. They tell you what happens if you move along straight lines and how f changes along these straight lines. But they do not tell you what happens if you move along curves, right? As you can clearly see in this example. And this is a problem, for instance, for the chain rule, right? So whatever happens, it should be the case that this curve t squared should be differentiable. Well, we actually know how to compute its derivative. And it must be, right? So we presume. There are a new notion of derivative encompasses the derivative that we knew how to compute before. However, you look at this example and you see that the chain rule miserably fails. I mean, it's not only that the chain rule doesn't work, it's that f is not, it's not even that it's not differentiable. It's not continuous. So that's a very serious problem with these Gato derivatives. And luckily we have a second definition, which comes from another intuition, from another perspective of derivatives for one-dimensional functions. So basically, directional derivatives try to define a higher dimensional notion of derivative by saying this. So look at the function f along straight lines. Straight lines are like the real line, so then you define things as if you were the real line, right? We're going to look at a different perspective now. This is a fact that can easily prove that a function f is differentiable at x0, so let's pretend f is a one-dimensional function, right? So, and it has this shape, and here is x0. So basically what this statement here is saying is that a function is differentiable at a point if it has a good affine approximation at that point. What's an affine approximation? An affine approximation is an affine function is a function that's given by a straight line, right? Whose graph is a straight line. So the form a plus b times t. And a function is affine, so f is differentiable at x naught if there is an affine function such that if I look at f of x0 plus h and I subtract f of 0 of h, where this is a affine function, divide by h, this goes to 0 when h goes to 0. So, okay, if f is differentiable, it's clearly that this is true. And if there is, right, so if f is differentiable, this direction is clear. So you just, you write f of 0 of h is just going to be f of x0 plus f prime of x0 times h. And it's a nice exercise to go in the other direction. Basically, what you show in the other direction is that if you have this, then it must be that a equals f of x0 and b equals f prime of x0. So if you like, we can say things in this fashion. We usually define derivatives in one dimension by limits in a specific sense. But we could also define derivatives in terms of these affine approximations. And in fact, that's like going the direction of Taylor series, right? Because this is an affine approximation. You can look at quadratic approximations or cubic approximations, and it gives you further terms of the Taylor series, which is a topic we're going to be coming back to later. But as a first step, we need to look at derivatives. And what Fréchet did was to look at affine approximations as the defining notion for derivatives in higher dimensions. So, okay, so remember our setup, right? So we have a function f defined over an open subset of a vector space V with values in another vector space, W. First of all, we need to understand what is an affine approximation, what an affine function from V to W. Well, it's a function of this form. F naught of x is the sum of a constant term with a linear term. So basically, an affine function is a translation of a linear function. And let me be clear, it's a continuous linear function, right? So a bounded linear function. So a function is affine if there exists an a and w, and a bounded linear operator from v to w, such that f0 of h is equal to a plus b times h for all h. And here comes a definition of the Fréchet derivative, and let me actually write it more or less differently. So if there exists a bounded linear operator b, such that when I look at f0 plus h and subtract this affine function here, I get that f of x0 plus h minus the affine function at h divided by norm of h. If this goes to 0 when h goes to 0, then we say that f is differentiable at a point x0 and that b is the Fréchet derivative of f at x0. And I mean, you could look at a different definition where you say if there exists a and w and they replace this guy by a, then it's the same thing. You only have to check that this definition with a. I mean, if this is true, then it must be that a equals f of x0. That's an exercise. But in any case, let's just say, okay, if this affine approximation is good in the sense that the difference between f of x0 plus h minus the affine function, this is less than h, well, that's smaller than h in the limit, then we say that f is Fréchet differentiable at x0, and this is the Fréchet derivative. Let me change colors briefly. So now we know what the right notion of derivative is. I mean, I haven't shown you that it's the right notion. The right notion of derivative is defined in terms of linear operators. So if you like, if you're looking at functions between Rd and Rk, Fréchet derivatives are going to correspond to matrices. If you're looking at more general spaces, well, they're linear operators. Here's an equivalent formulation, which is related to what we saw in the first slide, right? So the Fréchet derivative, if it exists, is this operator b, which we will write as f0 in LVW. And it should be such that if I look at a function, right, f of x0 plus h, it's equal to f of x0 plus b times h, plus a term that I mean, we write it O of h just to mean that this term, if you take its norm and you divide by the norm of h, this goes to 0 when h goes to 0 in v. I mean, it's really the same thing, right? Because this is saying basically that if I look at the difference between this and this, when I divide by the norm of h, this goes to 0. But this is sometimes convenient. It's sometimes convenient to write things in this way. We're also going to use the notation of calling this a remainder term. We'll use r of h sometimes. Okay. So we're going to now, to finish this video, we're going to prove some very basic but very important properties of this notion of Fréchet derivative, right? In the next video, we're actually going to learn how to compute these derivatives. But for the time being, let's just stick with the abstract definition because this is important for us. So these properties are here, right? So we're going to show that if f is Fréchet differentiable, then it's Gâteau differentiable, and we can compute the Gâteau derivative in terms of the Fréchet derivative, right? Gâteau is a directional derivative. We're gonna see how this notion, it's very abstract, right? It's defined in terms of linear operators. Nevertheless, if interpreted in the right way, then we can see that this notion really generalizes the usual derivative for functions from R to a vector space. And as our final result, we're going to prove that this satisfies the chain rule. Okay, so let's see how this goes. Okay, proposition 1 is that if f is Fréchet differentiable with x naught, then the directional derivatives all exist, and they're given by the Fréchet derivative applied to v. How do we prove this? Okay. Right, so if I look, I'm just gonna, I wanna show that this thing converges to this guy. So let me write things as follows. So I'm just going to write this as T D F X naught V. Right, and hopefully you agree with me. Well, this is, here you have the ratio, the usual definition of the directional derivative when t goes to 0. Here you just have t divided by t, so this gives you Fréchet applied to v. And we want to show that this is 0, right? So first of all, I'm gonna assume that v is non-zero, just because, as we noted before, v is 0, the directional derivative is 0, and certainly this is true of the right-hand side, right? The linear operator applied to 0 is 0. And why do I want this? Because I want to write this in the form that we know how to operate. So let me call age of t to be t times v. And notice that for t different than 0, this is not 0. So I'm going to write it like this. So f of x naught plus age of t minus f of x naught. Now I use linearity to move the t inside here, right? So t times df applied to v is the same thing as df applied to tv. And that's age of t. So I'm going to divide by the norm of age of t, but this is not really what I have in the denominator above, right? So I have to multiply by age of t and divide by t. So now let's look at what happens. Okay. First of all, when t goes to 0, this guy, age of t, goes to 0. And this thing here depends on age of t. So the definition, let me go back quickly. The definition says that if I take f of x0 plus h minus f of x0 minus, well, there's a plus here, but it could be a minus, right, if I remove the parentheses. Oh, sorry. And, right, if I look at this, this should go to 0 and age goes to 0. But here it is. This age, right, this guy here is going to 0. So this expression is f of x0 plus age of t, whatever. I mean, it's an age that depends on t, but it's going to 0. Minus f of x0 minus derivative divided by the norm. So this guy, when t goes to 0, plus, this goes to 0. And what about this other term? Well, this other term is simple, right? So age of t, t times v. So the norm of age of t, it's t times the norm of v. So therefore, this term here, right? So this term, let's say 1 goes to 0. And this other term 2 is equal to norm of v. So I have the product of the norm of v, right? So I have the product of the norm of v by something that goes to 0. Therefore, the whole thing goes to 0. And we're done. We've shown that this, what we wanted to show is that this limit here is 0, and now we've shown it. But as an exercise that allows us to prove that the Fréchet derivative is uniquely defined. There can only be one linear operator that satisfies this definition of Fréchet derivative of x at x naught. Why? Because we can compute this linear operator by computing the directional derivatives, right? So if we know there's such a linear operator, then we can compute this operator applied to v for any v in terms of directional derivatives. Directional derivatives are limits, and therefore they're uniquely defined for each v in each x0. So this is an exercise. I mean, it's a good way to check how well you understand the definition. So, and there's also a useful proposition in the sense that if you don't know that f is differentiable, it is a good idea to start by computing directional derivatives or even partial derivatives, as we're going to see later. And the reason is this. So when you compute the directional derivatives, it should be that they have the form linear operator, bounded linear operator, applied to v, for all v. So if the directional derivatives are like that, then you know how to guess who the Fréchet derivative should be, and then you can try to prove that it's actually the Fréchet derivative. That's one methodology for computing Fréchet derivatives. But okay, so it's nice to know because these directional derivatives are usually easier to compute than the Fréchet derivative, though we'll see ways to do it. Okay, now we have to go back and settle this issue of the relationship between the usual derivative and the Fréchet derivative when the linear space, the vector space V is the real line, and you use a subset of the real line with x0 belonging to U. And we have these two competing definitions, right? So the usual derivative is this guy, this limit that we are all used to. The Fréchet derivative is some linear operator from R to W, such that if I compute this expression, this goes to 0 when h goes to 0. So you can see there's kind of a mismatch here. It's a fixable mismatch because, but the mismatch comes from the fact that in principle the usual derivative lives in W, whereas the Fréchet derivative lives in this space of bounded linear operators from R to W. And therefore it's going to be very important for us to note this point here, that basically the space of bounded linear operators from R to W is essentially W. And what I mean is that the two are isomorphic, or isometric actually. And this is the content of this proposition. I'm going to prove to you that there is a linear bijection between W and L or W. It's a linear bijection with linear inverse that preserves norms. And so this means that these normed vector spaces, they're essentially the same, because I can make their elements correspond in a way that preserves norms and preserves all the linear structure, the structure of products by scalars, sums, differences, whatever. And I mean, this is perhaps a first point in this part of the course where kind of we have to overcome our fear of weird abstractions, because this is an abstraction, right? So linear operators from R, linear transformations from R to a vector space, that's kind of weird, right? But I mean, and we have to get used to these things, and they'll become second nature to us, but we'll have to give ourselves time to get used to this. For the time being, it's good enough that you understand that these things work and you can check them every time. Okay, how do I prove this? So look, first of all, let's take a linear operator, a bounded linear operator from R to W. And let's note that, let me define W of t as the linear operator applied to 1, and to emphasize, let me say it's 1 from R, right? This makes sense, right? I have a linear operator from R to W. I can compute the linear operator at a specific point of R, which is 1. And I have this guy. And now I notice that for all lambda in R, if I compute t of lambda, that's equal to t of lambda times 1 R. Well, the t is linear. Therefore, I have lambda times t 1 of R. So lambda times w of t. The upshot of this is that if I know this guy, I know how the transformation acts over any lambda. So t mapping to w of t is injective. Two linear transformations, t and t prime, are equal if and only if w of t is equal to w of t prime. And there's more, actually. How do I compute the norm of a linear transformation from R to W? Well, this is the sup over lambda not equal to 0 of the norm of t lambda divided by the modulus of lambda. And this, I showed above, is a sup of lambda, not 0, of lambda w of t, divided by lambda, which is simply, this is a norm in W, right? So the scalar goes outside the norm of the absolute value, so this is exactly equal to norm of W of t. So you can see that this map that takes t to W of t, well, it's injective and it preserves norm, right? So the norm of a linear transformation is equal to the norm of its corresponding vector. And in fact, you can show it's a linear thing. So if you look at the vector corresponding to lambda t plus t prime, you just have to check it. It's an exercise. This is equal to lambda times w of t plus w of t prime. So it's a linear transformation. And the s that I mentioned above is the inverse of this guy. So it maps a w to a transformation I'm going to call t of w, defined by tw of lambda to be equal to lambda times w for lambda in R. So, okay, I'm not presenting this is more of a proof sketch than an actual proof, but it's one of these things that it's so obvious to prove that it might evade your powers of understanding for a little bit, which is why I'm definitely, I'm kind of on purpose leaving out some details I need to check, right? So really, what you have to get used to is that basically, okay, geometrically, what is this saying, right? So I have here my vector space W. It's very complicated. It could be infinite dimensional. But once I know what this linear transformation T does to one, I know that the whole image of the linear transformation is contained over this line. And vice versa, given a vector in W, I can define a linear transformation from R to W, right? So this is a guy now R to W, which simply consists of taking any lambda in R and multiplying W by lambda. What I claim is that the map that takes T to WT is linear, right? So T to WT, this is linear. It's certainly a bounded map because you can see that it preserves norm, so you can show that it's bounded. A bounded linear map from T to WT. I claim that this S is the inverse of this map. And it's, S is a bijection, and its inverse map, which I just drew over here, is a bijection. And this bijection, moreover, preserves norm, which is what I wanted to show above, right? So, okay, this might be a bit too much to swallow in one go, but again, right? So we have to overcome our fear of abstraction. This will become second nature to us. The important thing is that you understand that what I just told you makes sense, makes mathematical sense. And if your intuition still hasn't caught up with this mathematical sense, that's okay. You'll get over it eventually. You'll get used to this. Okay, final result of this video is the chain rule. Basically, what I'm going to show you is that if you have a composition of functions G and F, the composition can be, the Fréchet derivative can be computed as a composition of linear maps. And I really should write this down like this, sorry. Here I write like a product of linear maps, but that's, right, okay, I'm saying other things here too, because I'm saying, okay, I have a function f from u to, from u to w. And here I have f of x0. And then I have this other linear function from a set here, u tilde to z. And here I have g of f of x0. And this is z. And I want to show that the composition is well defined, at least in over a neighborhood of x0. And that derivative takes this form. Okay? So there's a bunch of things that need to be understood here. First of all, okay, let's start by trying to understand what's going on, right? So the Fréchet derivative, so for the whole time, I'm gonna call y naught to be f of x naught. So the Fréchet derivative of, right, so, and I should have said here, if f is differentiable, Fréchet, when I say differentiable, I just always gonna be Fréchet differentiable at x naught and g differentiable at y naught, which is equal to to f of x naught. Right, so, okay, just to start. So I have this derivative, it's a linear operator. So I'm gonna call it t, just to make connotation lighter. Linear operator from v to w. I have s, which is a Fréchet derivative of at y naught of f from w to z. I'm just going with the definitions. What is s times t? Well, that's a linear operator from v to z, that takes an element v of v and maps it to s applied to t of v. And this composition of linear operators, we usually write it as a product, right? Because in finite dimensions, this gives us a matrix product. And just like I showed you that the matrix product is a bilinear function in this case, because I'm taking this thing is also bilinear, and it satisfies this inequality here. So as a linear transformation to v to z, s times t has a norm that's less or equal to than the norm of the product. So this is something that you need to check, perhaps once in your lifetime. It's the same proof that we showed for matrices. So there's nothing mysterious here. But it's nevertheless an exercise. In particular, this implies that this product of bounded linear transformations is a bounded linear transformation, well, now from v to z, right? So, okay, at the very least, this is well defined. And now there's the issue that I want to compute. I want to define this composition of f for a certain subset of u that I'm going to call u hat to z, with u hat open and x naught belonging to u hat. So I need this because I can only define derivatives of functions defined over open sets. But that's okay. And that's also not an exercise I'm going to leave for you. Of course, the problem is this, so that f is defined over an open set U, which, so this is space V. Now it maps to W, and it maps to some set here, which is f of U. And now G is defined over a different domain, which maps to G of U tilde in Z. But so basically, to make sense of everything, I need to look at the intersection of these guys, this is a set U double tilde, and I need to look at its pre-image, and that's going to be U hat. So sorry, the drawings are a bit funny. And we have to use that the pre-image of an open set is relatively open in U, and therefore it's an open set of U. And moreover, because we know that f of x0 belongs to U tilde, that's part of our assumptions, then U hat contains x0. Okay, so my point is that by restricting the domain, I can make sure that the composition is well defined. That f of x for x belonging to U hat belongs to the domain of G. And I can also make sure using continuity of G and F that U hat is open. So yeah, yeah, that's right. Oh yeah, sorry. Yeah. Is this correct? Yes. Okay, and now I actually have to prove the theorem, right? So remember that I'm gonna write it here on top again. S is equal to G y0. Y0 is equal to f of x0. And I want to prove that the Fréchet derivative of the composition is what I'd like it to be. This should be, right? This is what I want. G of f of x0 plus s times t times h plus a remainder term. And this remainder term should be O of h, right? So it should be, when divided by the norm of h, it should go to 0. Okay, here's what we can write, right? So let me call delta of h, right? So, okay, this is what we want. Let me call delta of h to be equal to f of x0 plus h minus f of x0 minus the Fréchet derivative th. Okay? Then I have that G of composed with f computed at x0 plus h. What is this? So this is exactly equal to G computed at x naught plus h, but that's f of x naught plus th plus delta of h. Right? Now, okay. And, right, so, and I have that G of f of x naught plus th plus delta of h. This is equal to f of x naught plus s times th plus delta of h plus a remainder term, which I'm gonna call, let me call it the remainder of G computed at th plus delta h. Okay. Now the question is, what happens when h goes to 0? Okay? And by answering this question, I'm going to descend what goes on here. So, right? So I have this thing, and I know the remainder behaves well. So I'm using the fact that G is Fréchet differentiable, so I have a well-defined remainder here, which, if I have vectors that go to 0, and I divide by their norms, the remainder goes to 0. Okay. So what should that be, right? So how do I use that? Okay. First of all, okay, when h goes to 0, I have the following. So remember that t, the Fréchet derivative at x naught, it's a bounded linear operator from v to w, therefore it's continuous, therefore t times h goes to 0 in v. And 2, I have this delta of h, which is f of x naught plus h minus f of x naught minus t plus h times h. And therefore, delta h is this little o of h, right? So divided by this thing here goes to 0 as well. Sorry, I made a mistake above, right? Because t times h is an element of w for any h, so this goes to 0 in w. Okay. So notice that since g is Fréchet differentiable, I have the following. So, okay, let me point this out now. Okay, so I have g of f of x0 plus th plus delta h minus g of f of x0. So this is y0, by the way, right? So, right, so in particular, I know that delta of h has to go to 0 as well. Right, so because if delta h divided by something that goes to 0, then even more so when I don't divide. And s times th plus delta h this whole thing here divided by t times h plus delta h z. This whole thing goes to 0. Sorry, this is a norm in w when h goes to 0. That's just because I'm just using the fact that g is Fréchet is differentiable, Fréchet differentiable at y0, which is f of x0. Of course, when I write this limit, I'm being slightly imprecise. It could be that the denominator here is 0 for certain values of h. So let me just say when h goes to 0 and th plus delta h is different from 0, so if you take any sequence of h's satisfying these two conditions, then we're in good shape. Of course, we have to fix that later, but we're going to see that's not a problem. Okay? But let me first deduce something from this. Okay. What I really want to look at is g at y naught y naught plus g of f, g composed with f x naught plus h minus g of f of x naught minus s times t times h, everything divided by the norm of h. Okay? And how am I going to deal with this? So I want to go back to this expression that I had before. So I'm going to add and subtract stuff. Well, first of all, this is exactly g of f of x naught plus th plus delta h, just by definition of the terms. G of f of x naught. Then I want to have here s times t of h plus delta of h. And then I add s times delta of h. And everything's going to be divided by age. Sorry, this looks ugly, but this is just what I have to add, right, to s delta h. There's norm in z. Now I'm going to break this in two. I'm going to break here using subadditivity of the norm. So I have that this is less than or equal to, okay, there is a quotient that's very similar to what we had in the previous slide. Sorry, g of f of x0 plus t times h plus delta of h minus g of f of x0 times z divided by h plus, then I have s times delta of h divided by h. So let me actually write this down over here. Sorry, I'm missing a term here, right? So minus s of t h, sorry, I have to write this all over again. So yeah, okay, so this is gonna be, okay, why don't I do it like this? I'm gonna give this this guy a name, this whole expression here a name, and this is gonna be psi of h, this whole coefficient with a whole norm, right? So I'm gonna have here psi of h, except that when you see what's in the previous slide, I have the denominator here that's t times h plus delta of h, right? Whereas here my denominator was this h, so I have to compensate for this. So I have to put t times h plus delta h divided by, norm in w divided by norm of h in v, plus s times delta h. And now I promise I'm almost done. And why I'm almost done? Okay, we know that this psi of h goes to 0 when h goes to 0. That's what we proved before. Okay, there's this caveat that we needed to look at sequences of h's going to 0 such that t times h plus delta of h is not 0. But notice that this doesn't really matter too much here, because if t of h plus delta h is 0, then this whole expression is 0. Right? So the denominator doesn't matter too much. I can just say, well, define psi of h to be 0 when this denominator is 0, and I still have the same bound, because in this case, this whole thing here is 0. So this is a trick I'm going to play often. So, okay, this thing, I'm only interested in bounding it when the denominator is not 0. When the denominator is 0, so I can just say it's 0, and this bound that I just wrote here is still valid. But okay, what is this thing? So let me bound this term. So this is less than psi of h times, okay, what is this guy? So this norm of t times h divided by norm of h is at most the norm of t. And then we have this thing which is delta of h divided by h. So I claim that this whole expression goes to 0. And why is that? Well, right, this first term here in parentheses. Why is that? Because this guy is going to 0 by the previous slide. This is bounded. It's just a constant now. And this goes to 0 as well. Okay, but this is just one term, right? I need to prove that this whole thing here goes to 0 when h goes to 0. Well, I'm almost done, because I have one term and now another term. I'm just going to use the following fact. So remember that not only t is a bounded linear operator, but also s. Therefore, this whole expression is less than the norm of s as an operator from w to z, divided by delta of h, which belongs to w, divided by h, which belongs to v. And now this is bounded, this is a constant, and this guy here goes to 0 when h goes to 0. So okay, the slide's a mess now, but you see what's going on, right? So I'm just, I wanted to prove that g composed with f at x naught plus h minus g of f of x naught minus s times e plus h goes to 0 when divided by norm of h. So what I did is I first computed this other thing here, and this is related to the Fréchet differentiability of g, right? The fact that this goes to 0. Okay, I proved that th plus delta h goes to 0, and therefore this whole expression has to go to 0. I have to be careful perhaps with this condition, but as we see later, that's not going to matter. But now this is almost, right, the denominator is wrong, so I should have norm of h here. But the numerator is almost what I want, so that's almost g of f of x0 plus h, right? So this is f of x0 plus h. This is f of x0. And here I should have s times t times h. I just have this remainder term, which I had to add and subtract to make things work. So that's what I have here. And once I do that, well, basically I have the quantity from the previous slide times something that's bounded. So this part goes to 0. Plus, well, s is bounded, times the remainder term. So if delta of h divided by h goes to 0, s times delta h divided by h goes to 0 as well, because s is a bounded linear operator. So you see that I use the boundedness of t here to say that t is continuous, therefore t times h goes to 0 when h goes to 0. And I use the boundedness of s here to be able to deal with this remainder term. So both boundednesses are important. And finally, what we have accomplished is, remember, right? So t is the derivative of f of x0, s is the derivative of g at f of x0, and we have finally proven this chain rule. We have proven that derivative of g composed with f is a product of linear transformations. In the sense, well, a product is simply the composition of linear transformations, which is another bounded linear operator. And that's it. So with this, I'm done. I finish. We've proven the chain rule. And I thank you for your attention. So next time, we're going to be talking about derivatives of functions from Rd to R or to Rk. And we're going to see that in that setting, derivatives look a lot more familiar, though we also have to be a little bit careful. So thank you.